All right, so we said our equilibrium constant and our reaction coefficients are the products taken to some powers over the reactants taken to some powers. Let's take a look at just a generic example. So we'll have AA plus BB in equilibrium with CC plus DD. And so the stuff on the right is our product. The stuff on the left is our reactants. And so we can write a K for this. And so we can say it's products taken to their coefficients over reactants to their coefficients. So it's going to be the concentration of one of our products, C, to whatever its coefficient is, times the concentration of D to whatever its coefficient is, over the reactants taken to their coefficients, right? So A to the power of A, and then B to the power of B. So that's just kind of a generic example. Let's take a look at kind of real chemicals. So we have 2N2O5 decomposing into 4 NO2s and NO2. So we can write K, and we can do products over reactants. So in this case, it's gonna, one of the products is NO2, and it has a 4 in front of it. So we're gonna put it to the 4th power. Next up, another product we have is O2, and O2 just has a 1 in front of it, so it's raised to the 1 power, but since it's raised to the 1, we can just ignore it, that's implied. And then it's over the reactant, so N2O5, and so this has a coefficient of 2, and so we want to put a 2 up here. So overall, pretty simple. Check out example 13.1 in your book for yet another example. And so we call this stuff, when we're talking about the concentrations of components, right? Remember, these brackets mean concentrations. We call this Kc. Kc. The C stands for concentration. So we'll see other values or other types of K. And so this K value is constant for a reaction. So every different reaction is going to have a different equilibrium constant, and it's at a set temperature. So if you change the temperature, you change the value of the equilibrium constant as well. So we can talk about in terms of concentration. For gases, we have an analogous figure. So for all gas reactions, we can also talk about, you can talk about still in concentration, but you can also talk in terms of partial pressures. Partial pressures. So for example, if we have N2 as a gas plus 3H2 as a gas in equilibrium with 2NH3 as a gas, right now we're all talking about gases, we can talk about the Kp instead, where P is now pressure. So we're talking K is equilibrium constant, the P indicates that we're talking about pressures. And so we can say that it's equal to the partial pressure of NH3 to its coefficient, right? So this is a 2, so this value gets squared. This is the product, so it goes on top, and then we divide by the reactants multiplied by one another, right? So P of N2, this is a 1, so we don't have to put it to any other power. And then P of H2, this is to the 3rd power, so we need to put a little 3 here, right, to the 3rd power. And so these capital P's represent partial pressures, right? Partial pressures of the gas. And then the last thing to note is that Q and K, equilibrium constant and our reaction quotient, are unitless. So even though you plug in numbers, you'll get units. Q and K are actually unitless. And the real reason behind it is a little bit more complicated, but if you're interested, you can read up on that on your own.